First of all, I want to thank you all for coming here today to hear this presentation. And I will tell you just a little bit about what's up on this introductory slide. So obviously the ACM of Orange County, the Quantum Optics Institute of Southern California is my organization that I started in 2003 as the Optics Institute of Southern California. And some years ago I decided going into more quantum, so now it's the Quantum Optics Institute. On the right-hand side, the Optical Society of Southern California is kind of my professional home, like you guys are ACM. I've been an optics guy all my life, since like 50 years, since high school. And we are celebrating our 75th anniversary in June, on June 10th in Torrance. So if you're interested in that, I think there's some flyers on some of the tables, not enough for everybody, but OSSC.org. And soon we're going to have a Quantum Orange County Consortium. So that's in the early stages of getting formed. So I probably won't say too much about that after this, but and on the bottom right-hand side, QEDC is the Quantum Economic Development Consortium, is a national, actually an international organization now, started around 2019 by the federal government to support building the quantum ecosystem nationally and now internationally to some extent. So today, we're going to talk about what's different between quantum 2.0 and quantum 1.0. And I'll go over some of the core concepts, which include qubit superposition and entanglement. And what are quantum qubits? Some different ones, some of the landscape, who are some of the key players that are making quantum computers and sensors and quantum networks. A little bit about cyber security and networking. So that's really important because, as you'll see during the talk, quantum computers are going to be able to be very, I'll say, dangerous in hacking various entities, systems around the world. Quantum workforce development. One of my key reasons for doing all this is because people like you could be interested and could enter the quantum workforce. So I will tell you a little bit about that and provide some education and career pathways for people at all different levels. And right in this room, there's a great diversity of people, and there are pathways for all of you. Some future trends, quantum AI and machine learning will be talked about, and then we'll have time for questions and answers. So I'm going to try and go relatively quickly. So if you have questions, I'll encourage you to write them down or jot them down or something, and then we'll do the questions and answers at the end. So is that good? So I'm going to tell you a little bit about me. Why am I here talking to you? Like I said, in high school, I started out in astronomy. My dad took me to Kitt Peak literally 50 years ago. And I built a telescope in the fall of 1977. Those are my younger brothers. I had some Encyclopedia Britannica because we did not have the internet back then. So on the right-hand side, you can see I was at the University of Arizona in physics and optical sciences. I started a program, well actually there was a program at Irvine Valley College from 1992 to about 2007 I was involved. It went on. But after 2007, I started a program at UC Irvine on optical engineering and instrument design, and that's still going strong. SPIE is International Optical Engineering Society. I became a fellow of that organization, I don't know, about 5 or 6 years ago. Optica used to be the Optical Society of America, the Optical Society of Southern California. SPIE is the Society of Physics Students, which I was involved with in high school, and I love to continue working with those folks. And VitalLink is an organization here in Orange County that links academic K-12 community college students and schools with industry. So if you're interested in doing that kind of connection, I have their card. They're just vitallink.org. So in 2019, December of 2019, the then president signed in the National Quantum Initiative, and that was what set the United States on pulling together their quantum strategy and funding, and QEDC was formed out of that initiative as part of the law, and right now they're working on a National Quantum Initiative reauthorization in our federal government, and so that is available on their website, and hopefully they'll pass that into law and continue funding and help strategizing what we should be doing as a nation in quantum technology. So this is just a note. It says in April 14th, they got it out of the House and out of the Senate committees, so that authorization is starting to happen. The last 2 days, I was in San Diego, and a couple of my friends here were also down there at San Diego Quantum Convening. That is basically the state of California, from the governor's office and many other entities, universities, government labs, companies, trying to figure out what California's quantum strategy should be. And because I knew this was happening a day and two before I would be here, there was one slide I think that I added because there was something very interesting, many things that were interesting, but one of, I think, most important about quantum cybersecurity. So we'll talk about that a little bit. So what is quantum, and what's the difference between quantum 1.0 and 2.0? So things, of course, at the atomic level are very, very different than at the level, the macroscopic level that we experience in our lives. And so we've currently been in our modern civilization, all our computers and the internet and everything, transistors, all are quantum, what we call 1.0. Quantum 2.0 is going to take us, humanity, to a whole other level in our evolution as sentient beings. I think we're sentient beings. So,
if there are any of us left.
Yes. So I think that all of you, if you'd like, you can participate in the upcoming quantum ecosystem in California, nationally, globally, and out into space. There we go. So, about 100 years ago, quantum 1.0, quantum mechanics, was kind of brought into being by these people in this slide and many others. So you're familiar with, of course, Albert Einstein. He was very involved in quantum technology. Max Planck taught us about discrete entities at the subatomic level. Werner Heisenberg talked about the uncertainty principles, very famous for that. Niels Bohr, the model of the atom. Erwin Schrödinger with the Schrödinger wave equations and Schrödinger's cat, if you're familiar with that. And Marie Curie, she actually got two Nobel Prizes in physics, one in physics, one in chemistry, and many of the other people that attended this, 17 out of 29, got Nobel Prizes for their work in this area. So it's one of the most successful theories in human history, in science history, is quantum. So there were some mysteries. Why did they come up with quantum in the first place? Because there were things that they didn't understand, the experiments. They couldn't match the experiments with their current physics theories or classical physics theories. It's like atomic spectra, black body radiation, the stable atom. Why did not the electrons just crash into the nucleuses? Radioactivity and the photoelectric effect. Can't cover all of these today. We'll talk a little bit about atomic spectra and the photoelectric effect. So Isaac Newton taught us about the prism and the spectrum of light, and that was actually back in the 1700s and late 1600s. He wrote the optics, the theory of light, the treatise, and all that. And boy, this is glitchy. Why? Okay. Dr. Fraunhofer started looking at these lines in this focused spectrum and determining those lines are the fingerprints of the atoms that are emitting that light. So that's very important. Those are discrete lines. They're not continuous. Let's see if we can get this. Okay, so the transistor was developed. If I try over this side, maybe this will be better. The transistor was developed back in the 1940s, I believe. And the transistors, of course, are in our phones, telephones, regular phones, radios, monitors, computers, satellites, and even in your daily appliances. So that's when quantum 1.0 kind of got started. And what is quantum anyway? So here's just from Wikipedia, just to give you an idea of what quantum is. There are discrete energy levels, discrete values of these different atomic levels of electrons, and how many electrons can you have in an atom. And you can't have half a photon, 1.5 photons, 3/4 of an electron. They're discrete entities. Okay, you can't divide them up and have fractional entities there. So in this case, you can emit a single photon, and you can detect a single photon. If you can do that, and we now do that on a regular basis all over the world, you can do quantum things in kind of the next level of what we're doing. Quantum things are looking at those particular photons or electrons and looking at their states. The state of a photon might be its polarization. The state of an electron might be its positive, negative charge. And you'll see in a few moments about a qubit that you can actually do things that are kind of analog in a way about those states. So some very simple equations like Max Planck's photon energy equation, E equals h nu, and Einstein's E equals mc squared, that's relativity. So these two things have had little challenges throughout the years of getting together, but what I want to show is that there's some very simple equations that if you understand what they're trying to say, then you really got a head start in learning about quantum. So a laser, there are lasers all over the place. There's a laser in this device right here. There's a laser pointer. This happens to be a helium neon laser, which came before the laser pointers and the laser diodes. But all these lasers do the same type of thing. They change the energy level of an electron, and when that electron drops back to its ground state, it emits a photon, and you have many photons inside these like neon tubes, and they go between the mirrors, and you get the light coming out the other end. So that's a laser, and you have E equals h nu, that's Planck's constant. So these are all the kinds of things. And here's Bohr's atom, that's a model of an atom. It's a cartoon. Atoms don't really look like this, but we've been taught through, decades of education, and so people look at this and they go, yeah, that's what an atom looks like, but it's not. So we won't get into the details of that, but they're kind of more like cloudy energy things rather than particles. Now you can do experiments where we can detect particle behavior, and we'll talk about that in just a moment as well. So the important phenomena about the second quantum revolution and the technology and the phenomena that we use to build the new technology, like quantum computers and sensors and networks, have to do with what we call interference, and that's part of the wave-particle duality that we might have heard about when we took our modern physics course in college, if you did. Superposition, where you actually have these ability to have, well, you can see the red line is the sum of the green and the blue line. So sometimes the red line goes to 0, it's flat. That's when the peak and the trough cancel out of the green and the blue. So you have all these different opportunities to have different states of this function. And entanglement. Entanglement, in my mind, is the most mysterious type of thing in quantum, and I believe most of the professors and experts also have the same mysterious feeling about entanglement. So we'll talk about that in just a couple moments as well. Einstein called it spooky action at a distance, and he really kind of didn't believe it for a long, long time. So here's an explanation and demonstration of some of these properties. If you take an electron gun and you put it through, aim it towards these double slits, you'll get this interference pattern instead of just it's all going through one slit or the other and you just get one bar. And so that's an interference. And this is what happens on the screen. If you're shooting electrons through this double slit, you can see it builds up over time, but you get this interference pattern. And that happens wherever you do this experiment. If you're careful about doing it, this is the answer you get. So that's why part of quantum mechanics has been developed to at least mathematically construct this, and it works all the time. And so here's a couple of other ideas that kind of help teach about quantum. So superposition in a regular computer, a transistor would be 1 and a 0. It's on or off. It's like a switch. But a qubit or a quantum bit could be like a spinning coin, where it's kind of both heads and tails at the same time. And this other graphic on the right there is kind of like a skateboard kind of doing the same thing. It's just kind of, it's neither here nor there at any given time. It's kind of a combination of both. These are macroscopic versions of what we try and describe these quantum effects at. Probably not such a great way to do it, but we have to do with what we've got. We're human and we live at this scale. So non-locality, that's the really crazy thing. So let me try and do this, okay? Entanglement means that the state of one qubit, so let's say polarization, right? If you have vertical polarization or horizontal polarization and you have two entangled photons, they're connected. And one goes off the other way and they split apart and you don't know what polarization they are. And when you measure one, then you instantly know the other. It's not as if those photons had a given polarization while they were traveling. They didn't. But when you measure one, instantly the other one goes to the opposite polarization. This is very strange. It's kind of like if you had two gloves. If you took a box, you had a pair of gloves, a left and a right, and you put one in each box, and you sent it off to opposite ways. As soon as you open one box, you know the other one has to be the opposite. But again, that's not quite a good analogy because the gloves were what they were when you put them in the box. And that's not what happens in quantum. So you can entangle electrons, their spin. You can entangle photons, their polarization, or atoms, their charge. And if the entanglement is disrupted, then you can't restore it. You can't copy it. You can't clone it. So that's part of the cybersecurity we'll talk about in just a few moments. And by the way, none of these entanglements mean that anything is traveling faster than the speed of light. Even though their states are unknown and unknowable until you measure one, that information between the two did not travel faster than the speed of light. It's a very strange phenomena, and whenever I ask the experts, the professors, they don't know either. We just go with it because it works. And we can make computers out of it. So here's a lab experiment that kind of shows how we can do this experiment with entanglement in a lab. And I'll just say, in the beginning, you have a single photon emitter, you have some mirrors, you have a polarization wave plate that sets the polarization in a certain direction, and then you have some crystals, more alignment, and this device here, this PPO pair, is this crystal. And it takes that one photon and splits it into two photons of half the energy, twice the frequency, and then those two photons are separated, and then you measure them on these detectors, and you can observe one and instantly know the polarization of the other one. And it measures it, and it's correct every time, which is a little strange, but that's what happens. I want to get one of these experiments. I've never done it myself, but hopefully I'll be able to do it at some point. Maybe even close by here. So quantum versus classical computers. Obviously, you know what an IBM computer is, at least a desktop personal computer like my laptop. Your cell phone is a classical computer. Even high-performance computers. We were down in San Diego. They have high-performance computers, which look like very large, a whole bunch of computer servers in a big room somewhere. So that's not a quantum computer. It's our fastest and best computers that we have that are not quantum computers. And then we have quantum computers. So quantum computers look very different. And I'll talk a little bit more about this as we go. But this is what's called a dilution refrigerator. And the quantum processing unit is down at the bottom. And what this is doing is actually chilling and chilling and chilling and getting the quantum processor down to near absolute zero, very close, millikelvins, or depending on the type of processor, what's required, but very cold. Sometimes it's the coldest place in the universe that we know of. And it takes, like this one is basically one that's all enclosed. This one, obviously, the lady is working on it. A lot of electronics, a lot of environmental control. And so these standard computers, classical computers, they all use what's the quantum 1.0 effect, like tunneling, semiconductor tunneling and things. So here's some standard computer components. So you can see you have your interface CPUs, memory GPUs. You probably are all familiar with this type of technology. This is what a regular computer, classical computer looks like. So a quantum processing unit will likely operate in a hybrid configuration with standard computers. So you can have that human interface between the quantum processor unit and the humans. and up. So again, another little bit of a demonstration here. You okay there?
Yeah, can you unmute first?
Unmute?
Yeah, from the slide.
Okay, hang on just a second. I'm going to.
They lost the sound.
Okay, yeah, so we got it back. We got my audio wasn't coming through on the Zoom. So we probably have, what, about 20 people on the Zoom as well?
Yeah.
So basically, again, the classical on-off switch from like a transistor, and this is a block sphere. So basically, the qubit, you can have an on and off, 1 or 0, but it can be anywhere in between. Let's see, come on, you can do it. Oh, hang on. I need to bring this back. Sorry, just a second here. Oh, no. Okay, one moment, please, and we'll get this back up.
No, that's right. It can be either on or off. Both at the same time.
Okay, there we go. Yeah, so we can have this, we'll call it a block diagram, a block sphere, and you can have a 1 or 0 at the top, but you could, that vector can be anywhere on that sphere, and you can see this kind of slow motion where the vector can be kind of moving around. But in quantum technology, these things move actually very fast, and I think I can just press this button here and you'll get there we go. Yeah. So these things can move quite rapidly and change their direction, and that'll depend on the type of qubit that we were going to do. So we'll get into what are the types of qubits. So again, here's just another cartoon of the on-off, the classical versus the quantum, and superposition, entanglement, and the qubits. And the qubits down here, when they're entangled, they mesh together, they talk to each other, work together, and they're combined states. And so here's a little mathematical construction of what these qubits are looking like and how people have to deal with them when they're doing the math and the computations. And so again, you can see the 1 and 0 at the top. So eventually, after the computation on each qubit is done, then it'll collapse into a 1 or a 0 state. But there you have a little diagram of where it might have been in superposition. So what does this mean? Why is a quantum computer faster or more powerful or can do more computations than a classical computer? Because these qubits, a number of bits in a classical computer over here, you have one operation. But if you have like 10 qubits, you could have 2 to the n. 2 to the 10 is 1024. And you can see how quickly it rises up. 2 to the n, 2 to the 20th, 2 to the 30th, 2 to the 50th. And I won't say that number, but you can see how quickly it just exponentially rises, so that you can have so many more calculations with so many fewer qubits. And so an example of a 64-qubit computer can be 264 times faster than a 64-bit classical one, or 18 quadrillion times faster. 100 qubits can hold more states than all the hard drives in the world, and you can kind of see where this is going. So this is why people are so interested in building up quantum computers that have more qubits. So what are qubits physically? How do they make qubits? So there's multiple different ways, and this particular diagram comes from Dominique Walleman from 2022, the domain of 2021, domain of science, 5 years old, but it's still pretty accurate. So what we have, I'll just go through a few of them. Superconducting quantum computers are one of the largest, many people are doing that, and I'll show you a bit about that in a moment. Linear optical or photonic quantum computers, and trapped ion computers. So these are all different ways of making qubits in the quantum world, and neutral atoms and optical lattices. So there's a bunch of different ways to make them. I'm not going to go through all of these. I'll mention a few more and who's doing them. But for example, what are they? So several, here's just 3 different qubits: superconducting, trapped ion qubits, and photonic qubits. So you use superconducting circuits here. On the trapped ions, you're literally trapping ions in an electric field, and then you can manipulate those ions with a laser beam, a focused laser beam. And then these photonic qubits, those are using entangled photons, and they're putting them through various photonic waveguides, or now we call them quantum photonic waveguides. So there's different advantages and disadvantages for each of them, and different companies are going through developing these kind of systems at a very large expense, in the billions of dollars, just like Google, IBM, Intel, IonQ, Quantinuum, and these companies, Xanadu and PsiQuantum. These companies are spending literally hundreds of millions and billions of dollars developing these computers. And so just kind of diagrammatically from a physics standpoint, you can see superconducting computers use inductors, and they have these potential wells. Photonic computers have photon sources and detectors and tunable photonic waveguide systems. And trapped ion computers, again, they're using laser beams and electric fields to trap these ions in a row or in a lattice or a matrix, and then they manipulate them. And neutral atoms are also using optics and lasers to take these non-charged atoms or neutrally charged atoms and manipulate their states in a quantum manner. So these are kind of just cartoons of what these people are doing. And all these slides will be available for you. So, so these are some of the companies in the superconductor, neutral atom, trapped ion, photonic, and silicon spin quantum dots. So you'll recognize, of course, Google, IBM, Amazon. I don't know if you recognize some more of these, but these are all the companies, here's Intel, that are really involved. If you ever go to any of the quantum conferences or read any of the quantum articles, many of these companies are also working with universities, government labs, so there's a lot of collaboration, both nationally and internationally, among these companies developing these quantum computing systems. So here's another diagram of them, and one of the things that I want to share with you guys about is the speed at which these developments have been happening. And so on the top right here, I just pulled this off of a LinkedIn. This was just a couple weeks ago, and this particular post talks about the fact that the biggest quantum computer companies are also doing the hyperscaling. So what that means is they're building big data centers, and they're working to try and figure out how can they use quantum computers to escalate and make their data centers faster and more efficient, use less power, and end up having more computational power as well. So here's a photograph of Microsoft's latest quantum processing unit. They use what's called topological qubits, and they call it Marijana. I don't know why that name is, but what is it? So they touted, or they talked about a new phase of matter that is involved in this particular quantum chip. I don't know enough about that to really understand what they're trying to say that is, but there are many technical articles written about it.
In the previous slide, I have a question.
The previous slide?
Yeah. So can I ask the question or should I wait?
Well, let me try and get through some more, because there's some, these are really just kind of, I'm just trying to get through the overview to let people know there's all the major tech companies and computer companies are involved in this. And then I want to get to like the cybersecurity part, which is one of the reasons why people are doing this. Sorry, that was Google, Quantum AI. They have their chip. So basically, remember the chandelier kind of looking thing, the dilution refrigerator? So these chips go at the bottom of that. They all have to be very cold in order to operate, to keep the environment and the noise from the environment, the thermal environment, vibrations, everything, especially the thermal environment, very, very low. This slide is about a company called Quantum. It started in Silicon Valley, but they're building two huge quantum computer data centers, one in south side of Chicago and one in Brisbane, Australia. So they got a lot of funding from the government and from independent financial organizations to build these photonic computers. So this is probably one of the biggest single type of system that's being built all on one particular architecture. So it's kind of like they're betting that this is going to work really well. And that looks like a semiconductor wafer, but it's actually a photonic integrated circuit wafer used. They use the semiconductor manufacturing process to make these kind of wafers. But because they're photonic and they have light and photons in the waveguides, they actually have to have fiber optics, very high precision to test them. So instead of putting electricity into the silicon wafer like we do for regular chips, regular semiconductor chips, they have to have light from fiber optics going in there. I like this one particularly because about 10, 15 years ago I was working for a company that helped develop that technology, and so I thought that was pretty new. And we didn't know about quantum computing back then, but there were photonic integrated circuits that people were working on, so this company took photonic integrated circuits and helping to make their quantum computer out of it. So this is just a cartoon that I just thought would be a nice break for a moment. So there's a lot of fun in quantum computing. So this is quantum bits, quantum computer database search, and he talks about a particular algorithm that people use called the Grover's algorithm, which helps you go through a whole bunch of data and find the particular information that you're looking for very fast. So that's another good reason and another use case or a way to find use cases for quantum computing. And they just show, he was looking for his particular fish and using Grover's algorithm and a quantum computer, he could find it very quickly instead of looking through every little box one at a time. So, having got through all that, we're going to go to something that's a little more, I don't want to say interesting, because that's interesting too, but why is there such a global race to build quantum computers and then to look at quantum cybersecurity? So everybody knows that our current technology gets hacked all the time, and that's a problem. And there's a whole global industry on cybersecurity. So now the quantum computers are going to make that worse, because quantum computers are going to be able to hack our current encryption technology, intellectual property, and whatever people want to keep secret. So here's one of the key developments that happened. Professor Shor from MIT developed Shor's algorithm, back in the 80s, I think it was. And he came up with this idea and a theorem and an algorithm that said, if you had a computer that could factor a very large number into its constituent primes, you could break all our encryption technology, or our current encryption technology like RSA and elliptical curve. And that's because our classical computers can multiply two big numbers together and get a bigger number. But you can't take that number and factor it into its constituent prime numbers. So that's what our encryption technology is based on. Quantum computer using Shor's algorithm will be able to do that much more quickly. So on April 3rd, there was some papers written and published about the progress in quantum computing and quantum cyber security, predicting that the quantum computers able to do this will happen and come online much more quickly than anybody predicted. This was a professor at Harvard and another group at Caltech. So they figured that they could use as few as 10,000 qubits to do this. And now these papers, as the critics will say, and you can read about that in these different review papers, if you will, there are a lot of assumptions that these people at Harvard and Caltech made in order to come up with their prediction of when a quantum computer will be able to crack and use Shor's algorithm to hack our encryption technology. But while that's true, it doesn't, what we're trying to do and what many people, the governments and many cybersecurity experts and people are trying to do is get awareness out to a much larger community, partly that means you, to say, oh, maybe we should pay attention to this and learn about it so we can become part of the prevention in quantum cybersecurity. Because there's a lot of published papers about quantum computers and their development. And we in the Western part of the world, we think we publish stuff and everything's good. But not everybody in the world is publishing their progress on quantum computing. We don't know what it is that they're not publishing. That's because they keep it private. So we hope we know. Now, this organization I've mentioned before, QEDC, there's a strategy of how to do quantum cybersecurity. And there's kind of two ways to approach it, and you can combine those ways. One way is kind of more software and algorithms. And for a number of years, the United States government was saying, we're just going to work with the algorithms, called a post-quantum encryption technology, PQC. And many other people in the world were saying that they want to use the hardware, the physics-based method, quantum key distribution. So this QEDC kind of came up with a paper about a year, almost 2 years ago, and they kind of wanted to say, well, it's probably a good idea to do a hybrid version of both physics and math, QKD and post-quantum cryptography. So I think that people are kind of going in that direction now. They're doing hybrid solutions. And here's a National Institute of Standards. They actually put down some post-quantum cryptography in August 2024. So they had some algorithms that they wanted people to work with, and that's still going on. And then just a few weeks ago, there was another recommendation and a draft about how people should go forward with quantum encryption technology. So here's another, I'll call it a headline, a post from a person at HSBC. HSBC is a bank. So the banks are very interested in all this technology because financial assets could get hacked by an entity with a quantum computer that didn't tell anybody that they had the ability to do it. They just go and do it once they have the ability to do it. So what this graph is saying is that in 2025, the experts were talking about breaking RSA 2048 in 24 hours. When do they think that might happen? And how long could it happen? And so actually in 2024, they had this graph like this. And now the graph, the same review of all the technical data in quantum computers. It's about, I forgot what the PP stands for. 12 percentage points, I think, difference. So basically, the ability for the time it's going to take for someone to use a quantum computer to crack our current encryption technology is getting shorter and shorter every time they do the analysis. And so this person here is saying that PQC, just the algorithms, is not enough. So there's a lot of different points of view in quantum cybersecurity, but I think that there's coming to be some convergence on that. Talking about resilience, talking about the physics of quantum key distribution, and even using AI to monitor what's going on. So there's a lot of work going on in this quantum cybersecurity space. And so as I mentioned, I was at this conference yesterday and the day before, but particularly yesterday down in San Diego. We had a gentleman from Caltech, and they started a new company called Oratomic. And this is a bunch of people at Caltech and other very high-end physicists and scientists, engineers. We'll just call him Robert, as the Chief Technology Officer, and he gave this presentation. And what he said to us, first of all, he wanted to make sure we understood what a cryptographic relevant quantum computer, CRQC, cryptographically relevant quantum computer. What is it? It's something that can actually use Shor's algorithm to break a public key cryptographic message. Okay? So that's RSA 2048 or ECC 256. Those are the key main cryptographic things that we're using. And of course, the danger is some evil actor is going to try and steal your Bitcoin. He uses that as an example. Because Bitcoin is, a lot of people talk about Bitcoin and how safe it is. Because it has a very large market cap and people want to steal your Bitcoin. So how close is it? So he said in 2010, we thought that theoretically we would have to have 500 million qubits, and at that time experiment only had 20 qubits. 8 years later, they thought, 20 million qubits, and we were up to 200 qubits. So it seemed like it was a long way away before they were going to make a quantum computer that could do this. So everybody was resting easy. This year, now we think, maybe we only need 14,000 qubits because of all the progress that people have made with their quantum computers and with their algorithms and how they're going to use these things. And now we have 6,000 qubits in experiments. So there's a lot of details behind all of that, which I don't have time to get into. But perhaps if you're interested, a lot of the information, there's a lot of links on the website that I have. And so he thought maybe by 2028, there'll be a cryptographically relevant quantum computer that can hack these things. So that was the main takeaway for me from that conference. And because all my slides were already done, this was the only thing I wanted to add to let you know that this is where we're at with the global quantum computing and cybersecurity race. But he did say this at the end. He said that classical data samples, where we're using these massive classical AI data centers, when we have quantum computers, the quantum computers will take up much less space and much less energy and be able to process a lot more data faster than all these big data centers that people are building. So data science and machine language, machine learning, you'll be able to use a tiny quantum AI computer compared to such a big, massive one, and it should be able to predict better results faster. So the quantum internet is taking shape. So these quantum computers, they're going to actually be connected like our regular computers are, not all at once. It's going to happen very short, very small amount at a time. One university, one government lab, one private entity at a time to another. But it's happening. A company called IonQ they're on the New York Stock Exchange. They have quantum computers, they have quantum networking, they have quantum sensors, and they're a global organization now. Of course, Cisco, you guys have heard of Cisco probably because they're on the classical network all over the world. And they now have a quantum research lab up in Santa Monica, and they have other partners all over the world as well. And they just released something they call a quantum universal switch, because all these different quantum computers and quantum technologies are not like our current internet. Our current internet has standards all over the place. So all the different types of devices all connect to each other. So Cisco, they want to be in that way with a current, with a quantum switch. And so they disclosed this just a couple of months ago, maybe just a month or two ago. And I think I can actually run a little video for you.
Cisco Quantum Labs is pioneering the future of quantum networking with the Cisco Universal Quantum Switch, an innovation that preserves the integrity of quantum information, enabling seamless quantum communication. Here's how it works. A single photon carrying 1 qubit of quantum information enters the Cisco Universal Quantum Switch through a standard optical fiber. The photon arrives encoded to a quantum state converter, or QSC, as one of several possible modalities: polarization, time bin, or frequency bin. Inside the QSC, the qubit is converted into a format suitable for routing. The converted qubit enters the switch blocks, where the quantum information is routed to a selected output without being measured or destroyed. By combining QSC blocks with the switch fabric, the chip is fully reconfigurable and can route quantum information from any input to any output. With this, we can bridge quantum computers from any vendor, allowing them to communicate effortlessly and unlocking the possibility of heterogeneous scale-out of quantum computing. At the output, the quantum information reaches another QSC and is converted into the desired output encoding, independent of input encoding, such as polarization. The switch is non-blocking, allowing multiple photons to flow through the chip at the same time, each independently routed while preserving its quantum state, enabling flexible, scalable quantum networking. The quantum future won't be built by any one company or any one technology. It will be built by connecting them all. With this technology, Cisco is building the quantum internet. Learn more at research.cisco.com.
So, I will say that this is in part, some of it is done, some of it is still aspirational, but obviously Cisco is a very large company. They have a lot of resources, a lot of knowledge, and a lot of capability. And I believe that at some point, they'll be delivering these types of technology. And this fella here, Reza, he's going to have a webinar. So if you want to learn more about this, you can just go to Cisco Quantum and sign up for this webinar that's going to be on May 28th. I'll be on that webinar because I think it'll be very good and interesting to find out what they're doing today as opposed to when they put out that marketing piece there. Now, they have been working very closely with a company called QNet. QNet is based out of Brooklyn, New York, and they have, I think, 4 different quantum networks in operation right now, one in New York, one in Berlin. There's one in Albuquerque, New Mexico. I'll tell you about that in just a moment, and another one going in Montana, of all places, right? So this is what their quantum internet looks like in New York. So it's works with New York University. They're in there. Their particular headquarters is here. I think it's in the Brooklyn Naval Yard, and they have a facility over here in this building. Oh, that's the Brooklyn Naval Yard, and over here with QTD in this building. So they've actually run this on classical fiber in a very noisy environment. So it's my belief that they have a really good system, and I've been following their technology for a little while, a number of years, and I think that Southern California should get something like that. They call that Gotham Q, 16 kilometers of fiber. And then they just installed one in Albuquerque, New Mexico, and that goes with Sandia Labs, Air Force Research Labs. I think that's a college there and another college, and then they have their facility over here. And what would somebody do with a quantum network, someone might ask? So you can work on quantum security. So we've already talked about how important quantum cybersecurity is, and you can do that over a quantum network. You can talk about communications and synchronization. So timing is everything in these communication systems. So quantum timing is very important. You can network quantum sensors together, and I haven't talked about quantum sensors, and it'll only be a little bit about that today. And you can connect quantum computers together, and people think the future of the internet, or in part, might be quantum-based. So again, here's some other quantum technologies, research and development, algorithm development, telecommunications, defense, industries, energy, protecting the grids, and financial services. So these are just some of the real important users who want to do this. This is our friend Nettie. He's one of the co-founders, and this is what one of the racks looks like in Albuquerque, New Mexico. And there's another company, IonQ, I mentioned them. They have a quantum network in Chattanooga, Tennessee. It's run by the utility company EPB. They have a quantum center there. So this was the first one set up a few years back, and they've been operating it and expanding it to Oak Ridge National Labs, University of Tennessee at Chattanooga, and other local areas, and people can go in there and do their experiments on this quantum network as well. And in California, we have an entity called CNEC, which is the Corporation for Education Network Initiatives in California, and they operate one of the largest fiber optic networks, well, probably the largest in California, and they connect the University of California, California State Universities, the community colleges, libraries, K through 12 nodes, hospitals, research labs throughout California. So we're going to be talking with those folks about what we can do to start doing quantum networking here in California. There's a very few test beds right now, but we would like to get something more, like a public quantum network that people can learn about. And there is one already at the University of Illinois Urbana-Champaign. And I went there and visited them and talked to their people, saw their systems, and I'd like to show you a little bit about that one. That's their physics laboratory on the campus. And that's their public library down the road. So that's changing the rotation of a polarization analyzer. These are the photons going through it. And then back to the laboratory. So that's why the timing is very important. So I hope to be able to bring this technology here to Orange County, and our friends at UC Irvine at the Beale Applied Innovation Center and the Quantum Institute, the Edelman Quantum Institute. We have a representative in the back over there. We thank her very much. We would like to put a system over here, and then possibly in the Newport Beach Public Library or other places as well, for example, right here in a building like this. So you never know. As it turns out, this location where this plaza is was the site where Albert Michelson measured the speed of light in 1931. He passed away before it really got done. And the city of Irvine has a marker in the plaza over there about measuring the speed of light here. So this could end up being part of our Quantum Orange County. And we have people from Chapman University here. We would like to work with them, and I'll show you a little bit more about that. Kenobi Martin, UC Irvine, and it could be other places. So this project is just in the early phases. So if you're interested in this, let me know. There's also free space, so not just in fiber optics, but you can just do it in like with a telescope. And you can, and people do this with regular classical communications, so we can do it with quantum communications as well, from the top of a building to a different top of the building, using a laser source and detectors. We can do the same kind of technology, and there is a professor at UC Irvine that's doing this classically right now, and I've been kind of talking to him a little bit about doing a quantum version. And there's a professor at Chapman University. He just got there about 6 months ago, and he's setting up his laboratories. That's Professor Ibrahim Karimi. And I just met him recently. I guess he's not here today, but he knows about this. And he's going to doing a project like this, because what if there's turbulence? If there's turbulence in between those two telescopes at the buildings, you can actually take the turbulence out. And astronomers have been doing this for many years. It's called adaptive optics and active optics. So I had a good opportunity to do some of that earlier in my career, so I hope to be able to work with the professor over at Chapman University. And then there's satellite communications. So a number of entities on Earth, in China, and different locations around the world, NASA and different types of government agencies primarily, have been doing quantum communications in space. So that's also available, also happening. And this is from L3 Harris Company, and they and many others have been working on quantum sensors, both for things in space, for positioning, helping, instead of GPS, you can use, they call position navigational sensors. And there's just a lot of quantum sensors that don't have a lot of time to go into. The Jet Propulsion Lab has done a bunch of different sensors, but there are biomedical opportunities, weather opportunities, fire, all kinds of things that are going on. And I wanted to get into the workforce development aspect of this. So you can see on this chart, there are education and career opportunities in many different disciplines that are already starting to try and figure out how to use quantum technology to enhance and solve problems that they haven't been able to solve. So obviously in computing, quantum simulation, personalized medicine, finance, logistics, and many more. Code breaking, robotics, autonomous vehicles, quantum machine learning, biology, chemistry, climate, light harvesting, battery development, drug discovery. There's just almost, I'd say, an endless end use case, but there are some which are the highest priorities. And so here's a list that I have. So I'm not going to read down through all the lists, but you can see again, drug discovery, chemical reaction modeling, oil and gas, financial services, fertilizer, solar panels. So there's just all kinds of applications. So sometimes you can think of whatever field you want to go into, there may be a really good quantum application for that. Machine learning, this is kind of an interesting graph if you look at it. What's the difference between classical machine learning and quantum machine learning? So the answer has to kind of start with the superposition of states that we talked about. And you could do quantum processing on these states to help your machine learning go faster and more accurate and process more information in a much shorter time period. And pattern recognition has been one of the preeminent areas of this type of work. So there's images all over the world, all over the internet, you know, all kinds of cameras and sensors. So we have to analyze those images and find out what's in them and then classify them. So quantum computing can help with that. And again, the processing methods of classical versus quantum, and you can actually go from classical processing to quantum processing, and then you can go back again and get that information back to the classical machines. And just some examples are genetics, self-driving automotive, and financial investments. Companies like Microsoft, Google, and Honeywell, and Amazon, they're all very involved in investigating any of these, as is IBM. So IBM has many tutorials. Their website has a whole lot of different applications in different industries. You know, quantum AI. AI is enhancing how quantum is developed. Quantum will enhance how AI is used. And you can see here, like in manufacturing, supply chain and logistics is huge all around the world. So quantum is being looked at for those types of applications. And pathways for college students and career professionals. So what can you do to get involved? You go home from this presentation, what do you want to do? Well, I'll tell you what you can do. So you can go on my website and you'll see this book, Quantum Photonics from Optical Bench to Global Impact. This book was published in 2025, just last January, a year and a half ago. And in it, there's a paper that I helped write called Quantum Technician Skills and Competencies for the Emerging 2.0 Industry. So that paper was written for a special section for workforce development in quantum for the SPIE special engineering, optical engineering, because as you saw, a lot of quantum is from optical engineering and laser engineering and those types of technologies. So people with those skills can transfer those skills into optics. But other people that have other skills can also transfer those skills into the quantum workforce. So the idea is that no matter what your background is, especially if you're a technical background, if you're sitting in this room, hopefully maybe you're involved with computer science, data science, it's not a far leap to start learning about how quantum works in the industry that you're already in, that you already have skills in. So get interested, find a mentor, somebody who's in your field that may already started down the quantum path, but take action, do something. Because the quantum industry and the quantum ecosystem needs more people like you. So just a little note here under miscellaneous, under quantum news on my website, there's a McKinsey quantum technology report talking about the commercial tipping point, a QEDC consortium, global quantum intelligence. We have a representative from there here. I'll show you about them in just a moment. There's another group called HKA Marketing Communications. They're in Tustin. They're the only communications company, public relations company that's involved in quantum, and they have amazing resources as well. And there's others. I'll skip the others. Quantum Dragon and the Quantum Insiders, those are all good. My friend Doug Fink, who's here tonight, he's been putting out the quantum computing report for what, 10 years now or something? 11 years. And so it's really quite good. There's so much information coming out on quantum technology that it's really hard to do. Doug also gave a talk at the Newport Beach Public Library, I don't know, 6 months ago or something. And so that was very nice. And there's Hillary Kay and her colleague, Mike Kilroy of HK Marketing Communications. So they have a thing called the webinar series of Quantum Spin. So there's podcasts and all kinds of information. You can't take it all in, but take in a little bit at a time and start learning about it. And on my website, Quantum for Students, if you're a student, go on this webpage, right from the home page, Quantum for Students. This is a very nice little video. I won't show you now, but Q through 12 for, K through 12. So for students like that, and there's all these are all my curated links. So if you click on these, they should give you good information. If they don't, tell me and I'll fix it. So get involved, you know, find a mentor, take some action, go on YouTube. If once you start, it's just, you're going down a digital white rabbit hole, you'll never come back. And there's actually 3 new consortiums in California, Quantum California, they're the ones that put on the conference last couple of days. There's a Southern California Quantum Alliance, which has a bunch of universities and JPL and maybe some companies as well. And just a very small one that started about a month ago called Quantum City Irvine, and we're in Irvine. I don't think there's anybody here from that little organization now. They're very small, but I gave a talk to them on World Quantum Day, which is always April 14th. And there's a reason for that, but won't tell you. And hopefully we'll have Quantum Orange County coming soon. So with that, again, this is my contact page on my website. If you want to get some information, you can go on there or just send me an email. And I just want to thank you all very much for your attention. I hope it wasn't too much. What? Back up to the other one? Okay. Yeah. So,
All right, so we're going to go into Q&A in just a second, but I get to have the first.
I hope that was interesting for you.
Great talk, Don. Just hang out for just a second. I'm sure there's questions. First of all, I need to get a count of how many IEEE members are here today. Oh, 10. Okay.
You're going to grab us?
What's that?
You're going to grab us, yeah?
No, it's just a co-sponsorship, so we do this. Also, IEEE students, are there any IEEE students here?
Over here.
There. Oh, one. Just one? Okay.
IEEE alumni.
Huh? Alumni? How about ACM students? Miss anybody? Oh my God. Oh, one. Okay, good. Cool. Nice. All right, so with that, actually the one thing, Don, is we don't have remote mics today, so if you could try to remember to
Sure.
repeat the question just for
I will-
both of our recordings.
Yep, will do. Questions?
Yeah.
Yes.
So in one of the slides you talked about a company called D-Wave. And the
D-Wave.
technology- Yeah, and the technology they use is quantum annealing.
Yes, quantum
So-
annealing from D-Wave.
Yeah, so it's a controversial technology. Some people say that it's not a real quantum technology. So what's your take on quantum annealing versus the traditional quantum? And they actually have their IPO and they're like stock.
Yeah. So I know a little bit about D-Wave and quantum annealing. Matter of fact, the day I met Doug Fink in 2019, I think in June or something, we had a professor from USC who has a D-Wave quantum computer that he works on. And my sense is that, yes, there's significant differences, but it was one of the first systems that came out and commercially available, and it does work. So it gets results. Yes, it's different than all these other quantum computers that I talked about, but it doesn't matter to me. So that's my opinion. I don't know, Doug, do you have a thought on that?
Yeah, D-Wave is certainly real. It definitely uses the quantum mechanical principles that we talked about before. I think the thing to understand, though, it is not universal. It does not solve, for example, the Shor's algorithm for breaking codes. But it does have applications in optimization problems. And there are people who are using it in production in optimization problems. And it's sort of a small niche. Almost no one else is pursuing that quantum annealing except for them, but they seem to be doing quite well with it.
Thank you.
Thank you. Yes, sir.
One of the things that I see when I see a quantum computer in a lab is that it's gigantic.
Yes.
Any comment on miniaturization? Are we going to get to a circuit someday, an integrated circuit?
Yes. So what you see actually are the dilution refrigerators and all the control electronics. The quantum processor unit is relatively small. So For example, yesterday and the day before at this San Diego conference, there were companies that were explicitly discussing that technology that will make them much more miniaturized. So it's happening. It just depends on the specific quantum modality that people are using. Yes?
Is cooling required for like reducing the thermal noise, or is it some other reasons for all this refrigeration and cooling for them?
So, yeah, I mean, the thermal noise, that's why you have to cool it, but really the quantum states and the stability of those quantum states rely on that very, very cold temperatures for those that need to be at those temperatures. Yes?
Okay, for the fundamental principle, the real application of quantum technology is the quantum entanglement, I think. How stable the quantum entanglement is in real life.
So the question is, how stable is quantum entanglement in the real life? So I had an interesting conversation with the professor yesterday, and in general, if you were out in space on a satellite or something, and you entangled two photons and you sent them off into the different directions in the universe, if there's nothing there to interfere with them, then they will be stable for a very, very long time. For example, if you look at photons coming from other galaxies or something, they could be entangled, and since there was nothing in between the emitter and the receiver, then they would be fine. On Earth, that's maybe not the case all the time, but like I showed some free space optics and also in fiber optics. So at the QNet system in fiber optics, they're sending entangled photons through kilometers of fibers, and they're able to maintain the entanglement in those under New York City noisy environment. And so,
Very robust.
yeah, so they have what's called automatic polarization control, so they can maintain the polarization as it's traveling through the fibers. So it's challenging, but people are doing it. Randy.
So you talked about the number of qubits to solve these problems, but the other layer here is error correction.
Yes.
Okay, so you need both.
Yes.
And you can have all the qubits in the world, but if you're not, so is there an advancement since the last time Doug talked and we looked at this, sort of in the 90% maybe error correction, and it needs to be at 99 or better, or is it 99, it needs to be
So-
99.9999?
So let me repeat the question for the people on the recording. Randy was asking about error correction, quantum error correction, and how many physical qubits versus logical qubits or error-corrected qubits are needed. So the slides that I showed from the gentleman at Caltech who showed those slides yesterday, those were all error-corrected.
Wow.
Yeah. And I think that's right. Is that what you recall? I think.
Yeah, at Caltech was just very recent research.
Yeah.
Just came out like within the past 2 weeks, I think.
Yeah.
And they have come up with some new codes. The research that's being done in error correction is just astounding.
Yeah.
The developments that have taken place and the advances, and a lot of it's advancements in the algorithms themselves make the talk that I gave for you
Obsolete.
6 months ago obsolete.
Yeah.
But one thing to remember is that one of the biggest challenges in quantum computing and making them work is the inherent quality of these qubits is really, really low. That they will, you put them in a state and they may decohere in like 1 millisecond. So that's why you need much, much more extensive error correction than you have in classical computing. And that's why there's a lot of research being done on this. So that's the hope is that someone will be able to come up with a combination of making what's called the physical qubits better, so that inherently you're starting with better material, but you still have to put error correction on top of it. And between the two of those, you'll be able to come up with what's called a cryptographically relevant quantum computer. And that was the talk he was talking about. And we believe people will be doing it by 2028, 2029.
Yeah. Yes, ma'am.
So, the cryptographically relevant, what kind of resources does it take to create that? I mean, is it, does it need the whole US government or,
Well,
China or something like that?
no, I think that, I think the answer to that is independent quantum companies
Right.
are doing it, and they're doing it with some assistance from federal government and from other governments. And so it's really kind of a public-private collaboration. So early on in the talk, I mentioned about the National Quantum Initiative Reauthorization Act. So that law that they're trying to pass will include funding to help the private and public consortiums or the different companies. So the government always, they kind of put out, once they have the funds and the way that they're going to allocate these funds, then they put out solicitations, and then people have to reply to those, and they have to propose what they're going to do with the money. And many times that might have to do with collaborating with, there's now like 5 national quantum centers that the government has already been funding and is already up and running. So they can work with those agencies, they can work with different universities. And so it's not unlimited, and it's not even, I don't think it's insurmountable, because you're talking about some of the biggest companies in the world. Google, IBM, Microsoft, Amazon, Cisco. Yeah, so these people are working together in some real ways in collaboration. So a lot of the papers that come out, it shows you who's working together on these projects. And if there's government funding involved, it tells you what that is.
You want to start something?
Yes, ma'am.
So I know that both Australia and France have been doing a lot of research, and they have a lot of companies that are quantum related as well. So how do we fetch up to where they are? Where do you feel that we are relative to what they've been doing?
So I know Doug has published and done a lot of work in that. Matter of fact, in your presentation at the library, you do that, and you do that on your website and stuff. So, but I would just say in general, in my biased way, the United States is up on the top. But I don't know.
What does Doug say?
What does Doug say?
Yeah.
What's your current assessment?
The US is in the lead.
Yeah.
But I would say that the Europeans and the Chinese are not too far behind us.
Yeah.
And it definitely would be very, very helpful if the Congress passes that law.
Yeah.
that reauthorization act that
Yeah.
he was just.
Write your congressman.
Yeah.
But it's all, don't you think also there's a lot of bias against quantum with people thinking it's still way the heck out there? I mean, I know really intelligent people in this industry who are going, oh, quantum's,
Okay.
it's out there.
That's why I'm here today.
It's out there. Oh, I know that, but I think
And so,
everyone here knows that, it's people outside. When I
if
go
you
to
hear
other
people
conferences.
say that, you can tell them to go to my website, tell them to go to Doug's website.
Right.
This information is publicly available.
Right.
So
Well,
those
right.
people just haven't been paying attention.
Well,
And that's a big majority of the people.
Let me just say one thing. It is changing. There actually used to be more people maybe 5 years ago doing that work. But with all the advancements, all the announcements that have made,
I agree.
it's
with AI and everything.
shrinking. People will see, hey, this is real. You know. Now, and the one thing is, just one message I'd like everyone here to understand. If you are a CIO or a chief security officer at a company, this cybersecurity threat is real.
Oh,
It's
absolutely.
going to happen.
Absolutely.
And you need to start your program, what we call a quantum sync program.
That's not the right one.
You need to start it there.
This one.
It's not an easy
That
thing,
one
but
moved.
you may have thousands of places where you're gonna have, if you're a large enterprise at least, you're gonna have to upgrade the codes that you use, the encryption codes that you use.
Absolutely.
So you need to start now,
Right.
that's the one message that we give to
Right.
anyone we talk to.
Right, and the real reason I make the statement is because I was at RSA in the spring. There's a lot of extremely intelligent cybersecurity folks there. And I was talking to them and they're just like, it's still far off, it's still far off. And I'm going, with AI, everything that AI has been doing to, you know, increase things that are happening out there, what the bad guys are doing and whatnot, it's reduced that time frame exponentially. So it's not 2035 or whatever, it's now, like you said, I think
We
2028.
just put out a message to our clients that, we pulled in the data by 3 years. And the thing we said is that based on some of those new papers, really, that have come out within the past couple of months, what we see is that it's substantially easier to break what's called the elliptical curve, which is what's used in Bitcoin and all sorts of other things. It's much easier to break that than it is for RSA. And both are heavily used in the IT industry. But the number that he put there where he said was 14,000.
We need 14,000 and we have 6.
Yeah, that's all based on the elliptical curve.
Right.
But if you're using Bitcoin or a lot of smaller systems will use elliptical curve instead of RSA.
Right.
I believe that if you watch some of the business news, you might have heard them talking a little bit about quantum computing companies, particularly those that are on the stock exchange and stuff. A little bit here and a little bit there. I believe that, you know, we're not kind of in the middle of the year now. By the end of the year, you'll be hearing more about this cryptographically relevant quantum computers and breaking RSA and elliptical. And, you know, that's my hope. I hope that happens. I don't know, you know, people like QEDC, and if they pass the NQI Reauthorization Act, you know, some of the Congress people, senators that have been promoting that, they'll get up in front of the microphones and on the TV and start talking about it, and then you'll see things turning with respect to that. So, yes, sir.
Thank you so much for the presentation. It's very informative. As you mentioned, there's a ton of information, massive amount of information on this subject. And I particularly am interested in the AI combination with quantum. And is there any kind of certification that one can kind of sign up and learn and kind of is more focused on what's needed now?
Certification. So I guess there are some, like at MIT, and you know, there's a few of these types of things around.
I can, IBM has a Qiskit certification.
Yeah.
Yeah, that one is very popular.
What was
IBM.
It's called Qiskit.
Yeah, if you just do an internet search for IBM Quantum, you'll find it right away. Or even just quantum certificates, things will come up.
And those are kind of industrial acceptable.
You know, there are so many opportunities in the quantum ecosystem right now. That I think the important thing is just to go home and dive in, do whatever kind of internet search you can think of that's of interest for you. Go on my website, go on Doug's website. You know, there's others. Once you start searching for quantum whatever, your inbox is, you know, your search results are going to be coming up.
And, you know, the thing is too, is there's a lot of people in our industry that are out of a job.
Yeah.
You have to retool yourself and look at what's happening in the future.
Yeah.
And don't just say, oh, AI, because as you've been saying, it's going to be AI plus quantum. So if you look ahead in the future and start retooling yourself that way and training for that stuff, you will have a better opportunity and chance to get a job that way.
Yeah, definitely. Yes, sir.
One thing you've been talking about is how quickly we can crack some of these algorithms.
Yes.
But it isn't so much how quickly we can crack it in real time. A lot of this stuff that was encrypted has been stored.
Yes.
Especially by foreign governments.
Yes.
And they're going to crack it whenever they get the opportunity to do so.
Yes.
There is an NSA algorithm that supposedly is quantum safe.
Yes.
What do you think of that?
The NIST algorithms? Yes. So, you know.
NIST, I meant, not
Yeah,
NSA.
no, that's, and I had a slide of those, and, you know, you need to talk to your cybersecurity experts and get them to, you know, start implementing something like that, because that is definitely the first step.
You think they work? Are they
You know, that's
quantum
what-
secure is the
So,
question.
so the people at NIST, and many others have said, you know, it's better than nothing for
I was
sure.
gonna say, what's the other option?
And, yeah, I mean, I'm not an expert in that area, but I leave it to the people that are experts, and there's many of them, and there's even some right here in Orange County or around, you know, in Southern California. So, if you have any questions, if you want to find someone, if, like the lady in the back there said, if you're a cybersecurity information officer or something, I actually spoke with the gentleman at the Orange County Sheriff's Department who's in charge of that. You know, got him to get one of his staff people to start looking into it on a regular basis. So, you know, the governments, our federal government has been on this for a long time. They're trying to get it down to state governments, which, because our governor and our state government is, you know, pushing it right now, and we're trying to get it down, you get it down to the county levels, you know, and the companies. So people have to do it, or if they don't do it, then their data is going to be at risk.
Yeah, Don, so thank you very much.